welcome to the Photovoltaic to Electric Vehicle Charger Project by Team 22027. Tucson Electric Power is an ambitious company working towards reducing greenhouse gas emissions. Tucson Electric Power filed an integrated resource plan with the Arizona Corporation Commission in 2020. The Integrated Resource Plan is a plan for Tucson Electric Power to provide 70% of their power from renewable sources of energy and reduce carbon emission levels by 80% by 2035. One of the ways to help reduce carbon emissions is to promote the use of electric vehicles and expand the feasibility of electric vehicle charging stations. Currently, electrical vehicle charging stations on the market are interconnected with the electrical grid or have an external battery pack that are not always environmentally friendly. This kind of electric vehicle charging station technology is not available to consumers that are not connected to the grid, such as historical landmarks or national parks, where implementing the infrastructure to support most electric vehicle charging stations is infeasible and costly. Our client, Tucson Electric Power, is looking for an electric vehicle charging station that will take energy directly from solar panels and convert this into electricity to charge an electric vehicle. The design of this photovoltaic to electric vehicle power converter system is important because it does not require grid interconnectivity or battery storage and will improve the product availability to consumers as well as help reduce carbon emissions. Initially, our client proposed the following requirements: that the system shall be weather resistant to NEMA 3R standards, the system shall accept 600 volts DC by simulation, the system shall charge an electric car at least a level 1 charging rate with a maximum current of 80 amps and a maximum power of 80 kilowatts by simulation. The system shall operate at 60 decibels or less at 50 feet. The system shall not exceed an external temperature of 55 degrees Celsius. The system shall have a light indicating readiness to charge. The system shall be a scaled down prototype version that costs $4,000 or less, and that the system shall use an SAE J1772 electrical connector to the vehicle. After reviewing the requirements, we broke the system down into 4 subsystems: the charging circuit subsystem, the microcontroller subsystem, and the cooling and housing subsystems. Our first subsystem is the charging circuit. It is composed of a transformer, which is a 240 volt 3-phase delta-to-delta transformer, a high voltage circuit board, IGBT transistors, which are responsible for pulsing the DC current to simulate an AC current through the transformer, diodes that are used to regulate the output transformer current. The electricity is outputted to the car through the use of an SAE J1772 adapter. The circuit also contains power regulation, circuit protection, as well as voltage and current sensing at the input and output sources. And it's all controlled by the microcontroller subsystem. It contains components that are responsible for controlling the system. The main brain of this system is the Arduino Mega 2560 that is responsible for monitoring the system through the current and voltage sensors and adjusting it in real time. Next are the gate drivers, which are responsible for controlling the IGBTs through phase width modulation. And lastly, the buck converter, which steps down the voltage from the source to power all the secondary items. The housing was outsourced and tested to ensure that it met NEMA 3R standards. The closed-loop cooling system designed for this project is composed of 3 major components connected through a series of tubes. First is a water pump that pumps water on the system. Next is a cold plate that dissipates heat from the charging circuit into the water. And finally, the heat exchanger that dissipates the heat from the water into air that is blown through a series of copper tubes. To ensure the cooling system met the expected values, we assembled it and tested it using hot water. The original functional requirement for our system was to create a charger capable of accepting 80 kilowatts. After doing research, we realized that the transformer specifically would be much too expensive considering our budget requirement. We then talked to our sponsor and negotiated scaling the system down to 50 kilowatts. We did more research and realized that even the 50 kilowatt system will be too expensive. Finally, we ended up with a 5 kilowatt system prototype that we have presented today. Although our system now only accepts 5 kilowatts, it can easily be scaled up to the 80 kilowatt system that was originally proposed by exchanging 4 components. Those 4 components are the transformer, the heat exchanger, the water pump, and increasing the voltage capacity of the PCB board. One of the most important parts of this project was learning lessons, and we did a few of those. Number one, we learned that presentation is equally as important as the engineering, and we realized this because we worked really hard on the engineering aspect of this project, but we found when we came to present the project to an audience, they're often confused by our complexity and technicality, and that if we could redo it, we would go back and make it more simple so that the general audience can understand. We also learned to really look into the costs associated with items. We found that a lot of our items were imported from foreign countries and had tariffs and such and taxes associated with them that we did not account for, which caused our budget to get some issues, which we were able to fix in the end, but it definitely caused some stress intermediately. Next, start earlier than expected. For things like machining especially, we didn't account for too much time for machining, but in reality, machinists, and when you rely on other people, they can often take a long time. And also our PCB board was a huge struggle in time for us. And if we had started designing it earlier and ordered it earlier, we feel we might have done better in that aspect. And then finally, to wrap it up, our project was limited by our budget and the power availability that we had. But another team can easily take our project and improve it with another budget to scale up to the 80 kilowatt system that was originally requested. Thank you for watching.